So next up we have Andrew Swan, who will take us towards computable homotopy theory. Take it away.
All right. Okay, so towards computable homotopy theory. So I'm going to start off by just doing a two-slide introduction to computability theory for hot people. So computable function is computable partial function is a partial function that can be computed by a computer. Formally, this was something that was first defined by Turing back in '36. So it's slightly earlier than like the actual real computers, like this one, existed. Depending on what you mean by computer. One of the things that Turing showed in this kind of first work was that there's at least one function which is not computable. So this is the halting problem. So throughout, when I write the down arrow here, it means that the partial function is actually defined. So this halting problem says that it's a function which is 1 if the nth Turing machine halts or is defined on input n, and it's 0 otherwise. And then if you kind of define it this way, then it's you can show that it's not computable. So of course this is a non-constructive proof. This is using excluded middle to show that this is a well-defined function. Okay, but most of so-called computability theory is actually about non-computable functions. But we can still kind of talk about how non-computable or how computable a function is, and this is done with the notion of oracle Turing machine. So it's an oracle Turing machine. It has an extra bit of computational information. So it's an oracle which can it can use to get some more information from somewhere, and then it can use this to compute more stuff, possibly non-computable stuff. Okay, yeah, and it doesn't have to be non-computable, by the way. There's also this kind of practical example. So I think this is due to Swan, this example, that if you connect to a server over the internet, then this is like very well modeled by oracle Turing machines, because if you connect to Wikipedia, then you're making an oracle query for the page about Leuven, for example, and then you read the page, and then it have like a load of links to pictures, and then you make a bunch more oracle queries based on your previous the answer to the first oracle query, and then these would be asking for the actual data for these images that are mentioned on the web page. So the point is you can make multiple oracle queries, and each query can depend on the result of earlier queries. So what I'm going to talk about is a fancy new version of this kind of classic result by Highland. And so again, this is already in the original 82 paper introducing the effective topos, that Turing degrees embed into the lattice of subtoposes of the effective topos. So this is some kind of fancy higher version of that. And it's going to be using cubical assemblies and higher modalities. So cubical assemblies, these are just, you take the cubical set model of HoTT, or a cubical type theory, and then you do it internally in the category of assemblies. So assemblies is it's a subcategory of the effective topos, and you can think of it as some kind of simplified version of the effective topos. So it's a model of extensional type theory using realizability. And then, so these form a model of cubical type theory and therefore homotopy type theory, but they're combining it with realizability because they're done internally inside the realizability model of assemblies. Okay, and then in some joint work with Toichiro Mura, there's a kind of slight issue with kind of the most kind of direct definition, that it doesn't satisfy many principles that you might expect it to satisfy. So the one we looked at in this paper, so we gave kind of quite a general technique, but the kind of special case that we looked at was Church's thesis, which says that all functions are computable. So this is a kind of classic realizability thing, that if you work inside a realizability model, then you have this kind of funny non-classical principle that all functions from the naturals to the naturals are computable functions. Okay, and so this isn't kind of directly true for cubical assemblies, but you can do something called a reflective subuniverse that I'll talk about a bit more in a minute. And this can kind of, one of the many applications of modalities or reflective subuniverses is that you can use them to kind of adjust things up and kind of patch the cubical assemblies model so it behaves a bit more like assemblies, and in particular Church's thesis. Okay, and then for the kind of stuff I'm going to talk about later, it's kind of good to know that so in general, propositions can kind of behave a bit strangely inside cubical sets, but it's kind of handy to know that if you restrict down to like the special case of double negation stable propositions, then everything is kind of like very well behaved. And for example, the double negation stable propositions that you get inside cubical sets match up with the external notion of double negation stable propositions, and in particular you can use the same classifier for both. So it's just a laser pointer. Yeah. So if we have a classifier for double negation stable propositions outside, then the discrete cubical set on that is also a classifier for double negation stables internally in cubical sets. So that's kind of a useful technical thing that I think comes up later. Okay, so second technique is combining realizability with modalities, and so modalities can mean many things. And for this talk, modality is something which is constructed internally in type theory, or like particularly in homotopy type theory. So this is the approach in this paper by Weicker, Schulman, and Spitters. This is a great paper. I always recommend this paper to everyone to read. And they gave like several definitions of modality, and three definitions of modality, or four, I guess. And I decided this was like the easiest one to fit into one slide. So I'm hoping that everyone's already familiar with this. So I'm just going to quickly say a couple of things just to kind of fix notation. So I'm always going to be writing circle for the modality, eta for the unit. And when I say a type is modal if the unit is an equivalence, and a type is separated if every identity type is modal, and type is connected if applying the modality makes it contractible. So if you like, this is like contractible. So connectedness is like an orthogonal property to being modal, if you like, and know what orthogonal means. Okay. Okay. So how can we use this to talk about computability theory, and in particular Turing reductions? Well, in fact, we can define Turing reducibility for modalities in general. This ordering. So I think actually the opposite ordering to this is again already in the Weicker, Schulman's, Spitters paper, but I want to like change it by doing the opposite order, I think, to what they do, and like writing a little T here for Turing, like I'm doing computability theory. So it just says that the modality O is less than O primed if every O connected type is O prime connected, and by some kind of formal duality, this is the same as saying that every O primed modal type is O modal. Okay, and okay, and then this gives a kind of nice way of maybe thinking about this construction of nullification, again from the Riker-Schulman-Spitters paper. So we're given as input a polynomial, so a family of types, in other words, and then the nullification of this polynomial is the smallest modality according to this ordering, such that every type in this family is connected for the modality. So it's the smallest ordinal, so it's the smallest modality, forcing all these types to be convertible. And then they also showed in this paper that nullification exists, and assuming you have enough higher inductive types, and you can actually describe it very nicely as a higher inductive type. So I was talking about this as a kind of polynomial, and the nullification is actually very closely related to the free monad on the polynomial. So it has the same point constructors, but it just also has some path constructors as well. Okay, so so I want to specialize this a little bit more, and so so I want to say what is an oracle, and then kind of what is an oracle modality. So this is not specializing that much from the general definition in the last slide, but it is kind of specializing a little bit more. So we have a kind of fixed modality nabla. So actually a lot of the times for the kind of general theory, you can take nabla to be any modality, but here we want to think of it, for computability theory, we want to think of it as a modality of double negation sheafification. So this is going to nullify all double negation dense propositions. So the double negation dense propositions are the ones that we kind of secretly know to be true if we kind of cheat a bit and use classical logic, and so nabla is the smallest modality which forces these to actually be true. So this is a way that we can access the world of classical mathematics inside assemblies, and also inside cubical assemblies. And so in particular, this allows us to kind of talk about non-computable functions, such as Turing's halting problem. That in the first slide. Okay, so now what is an oracle? An oracle is a function. Well, okay, so first of all, we have A and B, and A and B are like actual kind of types in our kind of general universe U. Okay. And an oracle is a new function that gets added when we reflect down to the reflective subuniverse corresponding to nabla. Okay, so yeah, so in particular, okay, so you can show by some kind of formal generality that functions from A to nabla B, these are the same as functions from nabla A to nabla B. Okay, so this is saying that if you have two types A and B, then nabla A and nabla B are the kind of closest approximations to A and B that we have in the reflective subuniverse corresponding to nabla, and then so an oracle is a new function that gets added inside this reflective subuniverse. Yeah, and then to kind of fix notation a bit more, we can think of the elements of nabla B as being a particular kind of partial element of B. So namely those partial elements which are not in total. And then so I write down arrow to mean that it denotes, which means that there's an actual element of B in the fiber of the unit map. Okay, so the oracle modality on an oracle is just a nullification of this polynomial of the propositions that chi A is a total element of nabla B that is defined. Okay, and so so like nabla is is kind of adding all functions that you have in classical logic, if you like, and so so the oracle modality is the way to just take one of these functions and just add that function in a minimal way and no others. Okay, so it's a large sub-universe that contains a map chi, if you like. So largest sub-universe, smallest modality. Okay, and then and then for like practical reasons, it's convenient that using double negation and stable, we can show this nabla as the kind of right universe level, but I'll gloss over this. So some other like basic propositions. All of these modalities are below nabla. Just for like formal reasons, because we're only nullifying nabla connected things. Okay, and then if B is a double negation separated set, then so the way I define this denotes it doesn't have to be proposition, but if B is double negation separated set, then it is. So in particular, we can look at when B is like natural numbers or 2, for example. Those are the main examples. Okay, and then there's a special name for these kinds of modalities which are generated by propositions, topological modalities, and in particular that these are Lex modalities. And so this is saying this reflective subuniverse is itself a modal type, and we can use this to actually get a model of homotopy type theory. In the reflective subuniverse. Okay, that's a general result, by the way. So I think Creowin worked out the details on that. Yeah, okay. So when working with these guys, it's useful to have kind of 3 additional axioms. So classifier I've talked about. Kind of a fancy version of Church's thesis where we can have partial multi-valued things instead of functions, and kind of a strengthening of Markov's principle. So I'll skip through that because so I think the main thing I want to cover in the remaining 2 minutes, right, is to give like at least one example of a kind of non-trivial theorem. So this is well, it's not that non-trivial, but it's non-trivial enough, I think, to kind of illustrate some things. So this is kind of the first example that I came up with, and it's still like the best kind of illustration I have of the kind of thing I'm aiming for. And so this is using homotopy type theory to kind of say something about some kind of basic result in computability theory. If we have an oracle chi, we can look at the loop space of O chi n in the universe, and then this is the group of permutations of n computable in chi. And then we can apply nabla, and then this erases all the computational information and just leaves us the like the actual algebraic structure of the group. And then we can use this algebraic structure of the group to recover the Turing degree. So if these 2 groups are isomorphic, and these really are just like groups in sets. So if these 2 groups are isomorphic, then the Turing degrees are the same of these 2 oracles. Okay, and well, you can prove this directly If anyone knows a reference where this is done, please tell me. But I'm going to give what is definitely a new proof of this, and then it's combining this kind of modality computability stuff with hot stuff. So from computability theory, we're kind of using things, finite sets are always computable. So if you have a finite set of things in nabla, then we can show that everything in the finite set is defined with a kind of DOM negation outside it. So this is kind of saying that finite sets, so each finite set is computable, but it's not uniformly computable. So computable is saying that we have for all alpha f this thing. This should say alpha denotes, if you like. And then not uniformly computable, this is saying this is what the double negation is doing here. Okay. For infinite sets, this is definitely not true. So leave that for next exercise for the audience, and then we can use as an application of this strength conversion Markov's principle, we can show that. So we can't decide whether or not two permutations are equal, even using the oracle. But what we can do is recognize that if two things are different, if two equivalences on n to itself are not equal, we can recognize this fact computably relative to the oracle. And then so we can use this to take three things, E, F, and G, such that F is not equal to G, and show that either we can compute relative to the oracle whether E is not equal to F or E is not equal to G. Okay. So that's kind of basic computability theory, if you like, but it's definitely some kind of computability theory. And then from HoTT, we use this kind of characterization of groups by Buchholz, Van Doorn, and Riker. So I've kind of convinced myself that like any proof of this is going to have to use a Riesz product, either implicitly or explicitly, and in HoTT we have this kind of very nice description of Riesz product. So I think this is kind of mentioned in passing in the Buchholz, Van Doorn, Riker paper. So the important thing is I'm using this in the proof. I can, if you want to know the details, you can ask me afterwards. And I skip over all this. Okay, so there's so the idea is that this is a kind of start of some kind of more general stuff, and there's like a bunch of kind of questions you can ask about this kind of thing. So in particular, I'm kind of thinking about what other examples there are of modalities in cubical assemblies, and for example, you can ask if there's any co-topological modalities. Maybe there aren't. So there's lots of kind of interesting questions you can ask leading on from this. So yeah, thanks for your attention.
Thank you. Okay, despite your long 2 minutes, we still have a little bit of time for questions. Anybody has any? Okay, I can ask something. So, well, one of the slides you passed by was about other modalities, and I was curious. So, I mean, as you say, one has this less than or equal for all modalities, and here you're looking very specifically at oracle modalities, but do you see kind of potential for generalization using techniques from computability theory, but maybe on slightly different modalities?
Yeah, so something you can like try to do is construct modalities through some kind of computability arguments, like finite extension. So finite extension is like an argument in computability theory where you build up a oracle a bit at a time. So these things I skipped over, they're actually using an idea from like HoTT, which is so I think these are called like suspension modalities, where you have modality which is something's modal if and only if it's separated from another modality. So the reason I skipped over it is that it's not especially about computability theory. It's like a very, very general thing. But I found it quite interesting to think about it in terms of computability theory. So
okay, that's sort of what I was looking for. So I'll stare at the slide. Okay. Do we? Oh, we're all right. We expected to be starting late, and we somehow got on time. So now it's
I see. I just wanted to ask. So, can you go to the slide with the open problems, please?
Which one?
Oh, the open problems
Yeah.
slide at the end. Yeah, right. So, so the second one here, you ask whether the categories of cubicle assemblies is hypercomplete. Do you have something in mind where you want to use hypercompleteness for? Like, does it?
Oh no. I mean, I'd,
You're just curious.
I'd actually prefer if like they're not hypercomplete, and there'd be like more interesting examples of modalities, co-topological modalities.
Aha. Okay. Okay. I see. Thank you.
So I think Benno has a question if there's time.
So I was wondering, so you started with mentioning Heiden's theorem about how the degrees embed into the subtopuses of the effective topos.
Mm-hmm.
The theorem that you had, is that like an analog or like a strengthening of that result as well? Or is, I mean, how did you, do you have a version of Heiden's result?
Yeah, so I think there is an embedding now. So a while I wasn't sure if I could do everything internally, but I think now it's kind of working. So it'd be necessary in any case to take a reflective subuniverse cubicle assemblies, basically I think I can like hit it with enough nullification that I can do an internal proof that if one oracle modality is less than or equal to the other, then there's that natural like Turing machine, which an oracle Turing machine, which translates between them. If that makes sense.
Okay. Yeah. Thanks.
Okay. Let's thank Andrew again. You keep going.